many polymers that we use are actually natural materials. And one example of a natural polymer that has been used for many decades, many centuries, is rubber. And rubber, which comes from the rubber tree, is a polymer of the chemical isoprene. And that polymerization is actually done by the tree, and the crude latex, which is a very sticky liquid form of the polymer, just drips out of the tree when it's cut in the right manner. Rubber, of course, has been used for clothing. It's much better for boots rather than clothing, and it's not a good material for making fibers. One of the best natural materials used for making fibers is cellulose. Now, cellulose is a polymer of glucose, and glucose can polymerize in nature in two different ways. It can polymerize to form starch, which we can digest. We eat it every day in potatoes or rice or bread. And if it polymerizes in a slightly different way, then it forms cellulose, which is the principal structural material for all plants. And that cannot be digested by us. The difference in the way of polymerization is simply what we call stereochemical. It's a small difference in the three-dimensional structure of the polymer. So cellulose, the structural material for plants, can be a very good natural polymer, particularly from cotton plant. And cotton, of course, is one of the major materials that's used for making clothing. The fibers are produced naturally by the plant, and then they are spun and they are processed by the mills. In forensic terms, cotton is a problem because all cotton fibers are chemically identical. They are all cellulose. In addition, because they are a natural fiber and they're not produced by any chemical means, they pretty much all look the same. All cotton plants give fibers that are very similar. The differences with cotton come in the later processing in terms of when it's dyed. So if you have a cotton fiber from a crime scene, the most information you're going to get is from the dye. That means if you're going to commit a crime, the best clothes to wear are those made of white cotton. Another important class of natural polymers, more important than polymers of glucose, are the proteins. Now, there are about 20 amino acids which are essential for life. And the amino acid molecules all contain what we call a carboxylic acid group, CO2H. Adjacent to that, they all contain an amino group, NH2. There's one exception that does not. These two factors are constant. The 20 or so essential amino acids differ in the remaining substituent, which I've indicated as R. And that is what makes these amino acids different from each other. The polymers are formed by the carboxylic acid unit of one amino acid reacting with the amino group of another, and so on, making a chain. And you can create an extraordinary number of proteins because you can combine the different amino acids into all sorts of different sequences depending on which of these substituents are you choose and what combination of different substituents are you choose down the chain. The R substituent makes all the difference, and the structure and the function of the polymer depends on those substituents. So while cellulose is the structural material for plants, proteins are the structural material for animals. They provide our tissues, they provide our cells, they provide our hair. Hair is made of protein. They provide our fingernails, and they are part of our bones. Even though we say our bones are made of calcium, actually our bones are made of calcium phosphate combined with proteins. Our enzymes, that is the chemical catalysts that keep our biochemical machinery running, these enzymes are also proteins. They're very highly specialized proteins. And the antibodies that we talked about in our lecture on blood, these are also proteins. So our bodies use proteins for so many different functions. And our body can do this because these different R substituents on the amino acids gives us an enormous number of possible proteins.